Okay, let's dive right into this. Welcome to This Explainer, where we are going to explore something truly fascinating. We usually think of medical imaging as taking a static picture, right? Like a photograph of a broken bone. But today, we're looking at a dynamic, living process. We're going to see how doctors can actually watch your kidneys filter blood in real time.
Think about that for a second. How on earth is it medically possible to evaluate the complex plumbing of the human kidneys without ever picking up a scalpel? How do we see the invisible flow of blood and the precise filtering mechanics deep inside the abdomen, all while a patient is simply lying still? Well, the answer lies in the incredible science of dynamic imaging, and it's going to completely change how you view medical diagnostics.
Section 1. What is renal scintigraphy? You can basically think of this scan as the ultimate medical detective tool. A doctor will order this procedure when they have specific medical mysteries to solve. They might need to evaluate basic renal perfusion, which is just a fancy way of saying blood flow, and overall kidney function. Or they might be hunting down internal blockages using something called a Lasix renal scan, also known as diuretic renography. It's also absolutely crucial for diagnosing renovascular hypertension, doing pre-surgical quantitation before removing a kidney, or carefully evaluating the health of a brand new kidney transplant.
Section 2. Preparing for the scan.
Now, before we can track the journey of our radioactive tracer through a patient's body, we have to prep the system. And in this case, the prep is all about fluid dynamics. A well-hydrated system is absolutely essential for getting a clear look at the body's internal plumbing. So the checklist requires the patient to drink about 5 to 10 milliliters per kilogram of water. To put that into perspective, that's roughly 2 to 4 cups, and they need to drink it 30 to 60 minutes before the injection. They also need to void, or empty, their bladder right before the injection, and then void one more time at the very end of the study. This whole process just ensures that fluid is actively moving through the kidneys without backing up.
To actually see the flow, we need our tracer. The exact maximum dosage here is 15 millicuries of a very specific radioactive tracer called 99-MTC-DTPA. The patient is briefed, told not to move a muscle, and then this dose is given straight into a vein in the arm. The technique the technician uses here is actually really critical. They use a gentle push to deliver a highly concentrated bolus of the tracer. It literally needs to travel as a tight cluster to give the imaging a crisp, clear starting point.
Section 3. The tracer's journey.
Over a period of exactly 30 minutes, we are going to track this tracer through a pretty thrilling physical journey: perfusion, uptake, and excretion. To catch that initial super fast rush of blood, what's called the flow phase or angiogram, the imaging equipment essentially becomes a high-speed camera, snapping frames every half second to 3 seconds for the first minute. But for the dynamic phase, where we watch the kidneys slowly filter and drain, we switch to a much slower, patient pace, taking frames every 15 to 30 seconds for the next 20 to 30 minutes.
Section 4. Analyzing renal blood flow.
So this initial flow phase is essentially a rapid-fire diagnostic check of the vascular pipes leading directly into the kidneys. Take a look at this sequence of a completely normal scan. The tracer begins up high in the lungs at 1 second. By exactly 3 seconds, boom, the aorta is fully visualized right down the center. And by 5 to 6 seconds, both kidneys light up beautifully and symmetrically. Notice how the activity in the kidneys is roughly equal to the aorta just above the split. That symmetry is exactly what doctors want to see.
But contrast that normal flow with an abnormal one, like a renal artery occlusion. Honestly, you don't even need a medical degree to spot the problem here. Just look at the visual asymmetry. One side simply isn't lighting up at all. If we see this kind of stark difference, or if the slope of the arterial flow just isn't steep enough, it instantly alerts the doctor that abnormal blood flow is happening on that specific side. Basically, the pipe is blocked.
Assuming the blood flow is good, the physiological journey continues right along. Next up is the parenchymal phase. This is where the kidney tissue rolls up its sleeves and actively acts as a filter, accumulating the tracer. Depending on the exact agent used, maximal activity in the kidney tissues is reached at about 3 to 5 minutes. After that, the kidney basically acts as a drain during the washout or excretory phase. This is where the activity leaves the kidneys, hits the collecting system, and drains into the bladder by about 4 to 8 minutes.
Section 5. Reading the renogram curve.
Up until now, we've mostly been interpreting visual images, black clusters on a white screen. But doctors need highly precise data too, so radiologists translate this entire biological journey onto a mathematical graph called a renogram.
Simply put, it's a time activity curve. It plots exactly how much of that radioactive tracer is sitting inside the kidneys at any given second, all the way from the moment of injection up to 30 minutes later.
Let's actually break down one of these curves, which is often used in renal transplant studies to calculate a perfusion index. The red line represents the blood rushing in from the artery. The blue line represents the kidney organ taking up that blood. The perfusion index is brilliantly calculated by measuring the total area under the aorta curve, essentially the total volume of blood, and comparing it to the area under the kidney curve, right up to the time of maximum concentration, or Tmax. And when you plot different kidneys on the same exact graph, the story becomes crystal clear. The blue line is the aorta spiking nice and quickly. The pink line is a normal kidney, showing a sharp, rapid uptake right behind the aorta. But look at the green line. That represents decreased flow. You can see how sluggish and flat it is compared to the normal kidney. It's pretty amazing that a simple line graph can instantly reveal the compromised health of that organ.
Section 6. The final diagnosis.
So we've seen the images and we've traced the curves. But how do doctors conclude this analytical journey? Well, they use these precise visual graphs to calculate differential renal function, or DRF. They'll digitally draw regions of interest over the kidneys on the computer and generate the sum of the images from the 2 to 3 minute mark. Crucially, they use math to subtract the background noise of soft tissue and blood pools. This isolates the kidneys entirely, revealing the exact percentage of the total workload each individual kidney is handling.
And here is the crucial medical takeaway from all of this data. You have 2 kidneys, and ideally, they share the burden equally. Perfect ideal function is exactly a 50-50 split. If that fraction starts to drop, we have a problem. A value of 40% or less in one kidney is definitively considered abnormal, and it signals a major red flag for the patient's renal health.
It's truly amazing what we can see today without ever making a single incision. We can watch a bolus of liquid travel from an arm, down an aorta, filter through the intricate tissues of a kidney, and drain right into a bladder, all translated into a perfectly mapped timeline. Which leaves us with the fascinating thought to end our explainer today. If a simple graph and a radioactive tracer can reveal a single blocked artery in real time, what other invisible, incredibly complex systems in our bodies could we map with just a tracer and time? Thank you so much for joining me, and keep exploring.